The broadcast is now starting. All attendees are in listen-only mode.
Hi there, everybody. I will let Mark take it away.
Well, hello, partners. Thanks for joining us. I trust that we have a few people that are interested in this topic because I think it is a breakthrough science in a way that we could implement citizen science perhaps in places in South Africa. Chris Smith is our speaker today. Chris is a long-term colleague of mine. We've worked together for most of 15 years down in Arizona when we shared offices next to each other. And anyway, much of his career has been devoted non-contact ways of measuring stream flow. And Chris and the people he's worked with have done a phenomenal job of developing some techniques that can allow for measurement without all the expense of a full-time stream flow gauge, and that produces different information, but this can produce discharge measurements with a relatively small front-end investment in technology. So anyway, with that, I just for your benefit, Chris, I did show to a few people that video that is on the web page, and so some of the partners have had some exposure to this already, but we always like to hear from the horse's mouth, so to speak, on these things. So with that, Chris, please share with us what you've learned and developed here with these non-contact methods.
Well, thank you, Mark. I started with this LSPIV. Went to a workshop in Champaign, Illinois 3 years ago to learn this method because it's really a passion of mine using video to make measurements. So this method, LSPIV, uses a video camera to measure surface velocity. And that's a key component of discharge. The other component you need is the flow area. So when you go ahead and you compute a discharge measurement with this, you need the video either captured by a drone, which is probably the best, but you can also use a regular video camera from a bridge or from the side of the channel to capture the video that will be processed for the surface velocity. But it's key to know the stage and the channel geometry, because without that, you won't know the area. And so what I really want to do is kind of just stay on this slide for a few minutes and really go over what's necessary when you're making one of these measurements, and understand that I have experience in being frustrated because I didn't collect all the information necessary to do a full measurement. So I have experience to know that these are key components. So if you're going to use it for citizen science, it'd be really nice to go out to the site where you feel you're going to need the measurement and put in a staff gauge, and also shoot the channel geometry prior to the flow measurement or the shooting the video. And that's important because you have to have a staff gauge to read the stage value. And so when you're out there videoing, you could also video that staff reading, so you know what the staff reading was during that flow event. Then that staff is related to channel geometry. So the staff plate will give you the depth of the flow, and then you have the channel geometry so you can calculate the area. Then you use the video to compute your surface velocity, and then you convert that surface velocity with in the case that I've been using, a correction factor of 0.85, and that changes it to mean velocity. And so the mean velocity multiplied by your area gives you your discharge. And so that's very critical. When you do a LSPIV measurement, you have to calibrate the video. You have to orthorectify the video. And in the case, we have this canal here, and there's 4 red points that these are reference points that are needed to orthorectify this video. And so you need to know the distance between these 4 reference points. And so on the next slide, I'm going to go over. This is for the video camera itself. This is what's needed. You need at least 640 by 480 pixels and a minimal 15 frames per second. Camera mounted on a drone is really nice because then you're shooting straight down and you only need 2 reference points. You can have it in a fixed installation where the video camera is shooting the water surface from the gauge. You could be mounted on a tripod, on a bridge, or on the side of a channel. Handheld, you can do that. But you want to make sure that the video is as stable as possible. Now, there are programs that, if it isn't stable, will make it more stable. But it's really important to have stable video. You want to record at least 1 minute of video over the cross section or showing the cross section that you want to compute the discharge measurement at. And then you want to make sure, like in that canal picture, that you see both sides of the channel. That's critically, that is critical in this measurement because you need to have those 4 reference points to orthorectify the video. And in this case, you can see this is a low flow channel where you have 4 reference points. There's actually 6 measurements that you have to make. Each one of these colored lines represent a measurement that you'll need to input into the river software. And so this calibrates this video, and it gives it the right distances and the right size distance in the pixels. And so it's critical that you get these 6 measurements if you're shooting from the side or from a bridge. If you're shooting from a drone, which this is where it's really nice, is you only need 2 of these, and you only need the distance between the 2 to orthorectify that video. So I really like the idea of being in a drone above the cross section, shooting straight down. All I need is those 2 points to calibrate the video. The surface velocity is computed by analyzing the wave forms on the surface of the water, debris that's floating. And so what it's looking for is those features moving downstream, and it gives them a velocity associated with that movement. This is probably the most important slide, is this reference to this surfboard homepage. This tells you how to go ahead and collect the data and to analyze it. And it also uses not only the LSPIV, but it also has surface velocity that's measured with radar. And so it discusses how you can use this radar off of bridges to measure surface velocity, but it also discusses how to guidelines for collection of video for large-scale particle tracking, the LSPIV. This is a place where you can really get detailed information on how to do this procedure. Today, I'm not going to go in that much detail. I wanted to point you to this location because these are the how-to. This is where you can get the river software, and it will also tell you how to get the PIV lab software. And so this is a really good source of information to allow you to make these measurements, and it will also change with time. These are the people that are actually developing this method. This Frank Engel, who's field guidelines quick sheet. He's the brains of this. He's the true expert on how to use this method, and also everything in the background, how these programs work. So he's a great reference. So right now, I was going to open it up for questions because this is really, this particle tracking. This is where you would go to look for the guidelines on how to set up your cameras, how much video you need, how to analyze the video, how to use the river software and the PIV lab software. This is really where, if you're going to make measurements, this is the place I would go to and use, their suggestions on how to set things up. The rest of the presentation is going to be covering how we're using this method in Arizona to increase the accuracy of our gauging stations. And then I was going to show you also the steps you use in the river software and the PIV lab, and go through an example of how you would do that analysis. So if anyone has any questions on the particle tracking, this would be a good time to ask.
Thank you, Chris. This is Clara from the Sustainable Water Partnership. I'll be taking over the facilitation of the session from Liz. I said to you before, I will have a lot of questions, but this mostly comes from my lack of background in this matter. So I'm just trying to wrap my head around more what you've said and how the uses can be possibly applied in our region. But we actually do have a question from Rodolfo Camachos, who is the Chief of Party of the Sustainable Water Partnership. Rodolfo, I'm going to unmute you so you can ask your question directly to Chris. Thank you. There you go.
Hi, Chris. Hi, Chris. Can you hear me?
Yes. Good morning.
This is exciting. I'm looking forward to see the rest of the presentation, although I had to walk out in a few minutes. But I'm just curious to see if they have done any comparison of this indirect approach to actual rating curve that has been developed using colorimeters, etc., and how has been the differences between the traditional direct methods of developing a stage discharge curve.
Right now, this method is being developed. Frank Engel, during floods in March on the Missouri River, which is a large river in America, made comparison measurements. And they made seven of these particle tracking measurements in conjunction with using ADCP measurements, which is our traditional method now to make it. And the measurements compared within 1% to an average of 4 to 5% difference. So and Frank used a drone when he made the measurement. So we felt that this was really good news for calibrating the method. we also used it here in Tucson, and that's my example today, where we were at a gauging station. We had the opportunity to go ahead and fly the drone at the site where we have sensors out, and then we were also able to make a direct measurement, and that compared very well. The problem that I had is that you have to collect a lot of additional information. You need to have that set up ahead of time so that you can really accurately determine what that discharge was. And we weren't able to do that for this particular flow event, but it was close enough that I felt that it worked pretty well. But we're in the process now of collecting this information, so I now have 16 drone pilots that are able to go out during floods to make these measurements, and I was hoping to have a lot more of that information that you just asked for, but we're kind of in a drought, and so we haven't had any high flows, so we haven't been able to go out and make those measurements, but we'll be able to do it over the next year.
Thank you, Chris. Rodolfo, does that satisfy your question for now? Sorry, let me unmute you. Yeah.
Just a small follow-up question on this one. I know in Missouri there's big rivers, but I'm curious about the comparison of smaller rivers and smaller streams, because I mean probably there may be more error there than on a large river.
Well, the Missouri it's a large river. I think it was the flow, and I'm sorry, I'm stuck in cubic feet per second. They measured almost 300,000 cubic feet per second, which would have been probably 900 meters per second, cubic meters per second. So you can use it on big rivers. What's really nice about the drone is you can take it higher up, and then it can see both banks. And so it's been really an effective tool to use in these measurements, because if it's a small river, you can be closer to the water surface. You'll have more information. It'll probably be a better measurement. You can, if it's really big river, you can be up, 400 or 500 feet, maybe higher than that, and you can still be able to see both banks. So right now, I would say measuring, the 300,000 CFS is probably the greatest range that we'll have here in Arizona. So I was really pleased to see that.
Okay.
Thank you, Chris. Thank you for that answer. Can I also have 2 follow-up questions from there? And please, Chris, forgive my naivety in asking these questions, but it really comes from a place of ignorance on the topic.
Hey, don't worry about that. I'm just learning now.
Okay, I'm sure you know a lot more than I do. When you talk about, in your answer to Rodolfo, when you talk about the fact that you need additional information, what are you referring to? What kind of information, what kind of additional information you need to make the outcome of these flights and this sort of, camera-based monitoring more effective or more true?
It is, yeah, it's critical to have those reference points. If you're using a drone, it's much easier because you only need to have 2 reference points that you have to know the distance between those 2 reference points. And so that makes this so much easier if you use a drone. So if you're going out to a site, it'd be nice to know, and this is what we're doing right now. We're pre-staging our measurements. So we're selecting the sites that we can fly the drone in, and we're making sure that we have the reference points visible during the flight, so that we can see those in the video. So you have to, those reference points have to be visible in that video, because that's what actually calibrates it. So that's the most important thing. The second most important thing is you have to measure stage. You have to have a stage reading of that water surface, because that's the only way you're going to be able to accurately compute your area. So if you're going out, and let's say this wasn't at a gauge, or you don't have a sensor, if you had another person with you, what you could do is you could make sure that they set up 2 reference points, and then measure between those 2 reference points on one of the banks. You can also go ahead and mark the stage with some type of flagging for the stage that existed when you were taking the video. Then you would come back after and you would shoot that cross-sectional geometry and also that stage reading. And then that stage reading would give you the depth in that cross-section. So that would give you the area that you need. So you would use the video to give you the surface velocity, but you need this other information to give you the area flow. And so discharge is just area times velocity. So you have to make sure that you can orthorectify that video, and then you also have to be able to determine what that area was at the time of the flight, or time of when you took the video.
Okay.
Does that make sense?
Yeah, yes, it does. It will take me some time to fully absorb it, but for now it does make sense. Thank you. Thank you very much.
And believe me, I thought, the flow reference points, it seems like I always forgot one measurement. So it was the most frustrating thing. You come back with 5 measurements, you're supposed to have 6. So it's been a frustrating time. So with the drone, if you just use the 2, and the results are incredible.
Yeah, I hear you. Okay.
Clara, may I follow up?
Yes, please, Mark.
Chris, you've talked a lot about the drone technology, which I think, obviously has real power, and especially for larger rivers. But many of the streams, I think, in South Africa, we could benefit, are smaller and could benefit by having measurements, as in the video talks about using cell phone video. And you didn't mention that. Could you mention that?
You can use your cell phone, and but you have to have those reference points. You have to. You can use any type of video camera, but that video camera has to be seeing those 4 reference points if you're not using a drone. So let's say you're on a bridge and you're looking downstream and you're using your cell phone to collect video. You have to be able to have 4 reference points in that video that you can make these measurements, so you can orthorectify that video. With that video not being orthorectified, you can't compute the velocity.
Right. So establishing those data points is not a difficult thing, right? It's just a matter of driving some stakes in the ground and color them so they can be seen, and then measuring the distances between them, which can be done relatively easily on a small stream, right? Yes.
And then also having the stage reading at the time of the video and the channel geometry. Now, you don't have to have the channel geometry at that time, but you do have to have the stage. So that's why I'm saying if you put a staff plate in there, at least you'd be able to read that staff plate, so you'd have your stage. I would, if you're going to do this where you're going to have people go out, and I would at least have a staff plate there that allows you then to have the stage. Or, the person has to go out there and mark what that stage stage was during the video, and then you come back and shoot the geometry.
Yeah, so just in terms of application as a citizen science tool in Southern Africa, I think that will still require some sort of training and sort of selection of people within a given area or community to train and say, look, you know, you can do this, but this is what you have to provide us with. It's not just about going to the river and taking a video and then upload it onto a cloud. It's, you know, there is quite some preparation to be done. Is that correct?
Yes, and believe me, I've made every mistake possible. And
Sure.
so, yes, they have to be well trained, because, and they have to, it'd be nice if they could also process the video, because then they learn from their mistakes.
Yeah, so one thing that I wanted to ask though, so because like if you're measuring the flow and the velocity, and if you want to use it as a tool to monitor the rise of a flood, you know, like here sometimes we have flash floods, but sometimes you also have slow rise floods. So the point is, what I wanted to ask is if you have a certain amount of videos with those points, with those critical reference points already set up, you know, that you've done monitoring and you've trained the people and everything is flowing quite well, everybody knows what they're doing, very limited amount of mistakes for several months. By the time, say, a flood comes, can you, if you have the video that always measures that specific point in the river, could somebody go and take a video of that flood even without that reference points, because by now clearly they might be flooded as well, or it might not be safe to do that kind of preparation work? And would there be some sort of ability in the software or in the processing software to recognize the area and therefore use the previous reference points and for measurements, or not at all?
If you don't have the reference points, it's very difficult. You have to have that.
For each video, you have to have its reference points.
Right. I mean,
okay.
And the thing is there's other techniques at that point that you can use to compute the discharge. And that's a slope-area method that we use. But, you know, the reference points, they could be trees. You can have 4 trees. You can, as long as you can visibly see the trunks or whatever to make those measurements, that's fine. So, I mean, we use light poles. So there's many different types of reference points that you can select. There's usually something you can say. So, but if you really want to do, if you really want a good measurement, and that's what I'm at least trying to get you to do, you have to have these type of data so that you can produce a good measurement.
Yeah. Okay. Thank you for that.
Sure.
Yeah. Are there any other questions? Do you see any other questions from the participants? No? Okay. Do you want to carry on with the rest of your presentation then?
Yes, that'd be great.
Thank you.
Now, the way that we're using it in Arizona, because we're in a situation where a lot of the techniques that have been developed for the USGS, they just don't work in Arizona because of the sediment concentration. And so you can see in this particular slide, here's a dry channel, and then here's a picture of it flowing. And so a lot of the sites we may not be able to get to during a flow event because the road to this gauge is a channel, and so we can't access it. Or we'll have flow events that happen at night, and so we don't go out during the night to make direct measurements. It's too dangerous. So we had to come up with a technique called the continuous slope area method that allowed us to make measurements when we didn't have to be at the site. And so what I'm going to do is just go over this continuous slope area and show you how we're using the particle tracking to help verify and develop the rating for the continuous slope area. Because one thing that the continuous slope area doesn't have, we have to estimate the Manning's N, the roughness coefficient. And the particle tracking allows us to calculate that Manning's N. So it makes the continuous slope area process more accurate at that point. The slope area method is exactly what you had stated. A big flood comes, and then we go out and we look at the high water marks that are left from the crest of the flood. We'll measure those high water marks. We'll also measure the channel geometry in that channel reach, and then we'll use the slope area program to calculate what that discharge is. What I did want to point out here is the particle tracking measures the surface velocity. The slope area program measures the flow area. So from these high water marks, we can use the high water marks to give us the stage, and then we shoot the channel geometry, and that gives us the area of the flow. If we had particle tracking measurement to give us the velocity, then we could just use that velocity multiplied by that area, and that would give us the discharge. With the continuous slope area, what we do is in this channel reach, we actually put sensors. Now, if you were going to set up one of these sites, you could set it up with one of these sensors so you could use one of these types of installations that we have. Set up a sensor. It's a pressure transducer with a data logger, and it can almost store a full year of data in it. And then you have to have a barometer also with it. But it's an inexpensive way to operate a gauge. If you use this particle tracking to calibrate it, it's a very good way to measure stream flow. And it'll give you for that event, especially in streams that are dry most of the year, we can go and have these sensors out in the channel. If you had only one, that would be like a normal gauge. We put up to 3 out there so that we can actually use the slope area program to calculate the discharge. So we don't have to be out there to make measurements when we use this technique, other than to verify what that N value is, the roughness value. That's the only thing that we don't know. And so if we can use the particle tracking to give us the surface velocity, and we know the area, we can compute the discharge, and then we can use programs that will calculate what the N value is, and then we'll have a much more accurate gauge. And so in this case, this is an installation where we have 4 sensors. We have 4 locations where we shoot the channel geometry. We also, after a flow event, will come out and we'll survey the water surface that was left at the crest of the flood. This is to verify that the procedure is working. We'll also shoot the geometry of the channel if there was a change from the previous time we shot the geometry. So what we're doing is, through time, we're also measuring channel change, because whenever we can see a change in the channel geometry, we'll go out there and resurvey it. And so through time, we'll know what type of flow event caused the change in the channel, what the magnitude, the frequency of that. And so we'll have a better understanding of what type of flows make the channel change. The other parameter, again, is the roughness coefficient, the Manning's N, which is used in every hydraulic model. With this technique, if we use the particle tracking to give us the surface velocity, we can calculate that N value now. We don't have to use hydrologic judgment on how to determine that. So it's much better to have a way to calculate it. And so when you're selecting one of these CSA reaches, you use the same technique as a slope area. You want a straight reach, stable channel. And the beauty about this is a lot of times our gauging stations are bridges or other locations where the gauge has to survive. But the hydraulics in that channel reach may not be very good. What we can do is we can go to a really nice straight reach where we can go ahead and put these sensors in there. They don't have to survive. We want them to survive because they're collecting the data we need. But if we had a major flow and we lost them, we didn't lose the gauge. And we're not losing a lot of infrastructure. We're using low-cost pressure transducers. And so we've been running these in Maricopa County since 2004. We've only lost one in that whole time, and now we have 35 sites operating in Arizona, and so we're able to measure in reaches, channel reaches that are uniform, have similar shapes, similar areas. So now we're collecting information of a channel reach, not just a single cross section at a gauge. This shows the typical instrumentation housing. The one where the concrete and it's parallel to the channel bottom. It was a very high gradient stream where boulders were coming down. We needed this to survive, so this is an installation where we wanted it to be streamlined, and it did very well. All these installations survived all the flow events that have occurred. We put them in sand channels. We put them in channels that have boulders, many different ways to apply these. And now we have data all the way back to 2002. These sensors, they're non-vented, so we have to have a barometer with them. For each CSA section, we have to have a barometer, and we normally have three of the stage sensors in the channel. The battery life for these are 10 years. We use 5-minute data, so we have to go out to these at least twice a year. But if you use 15-minute data, then you have data collection capabilities for over a year. You wouldn't have to download this, and the accuracy of these sensors are 3/100ths of a foot. And then this is the location that is this is the pilot where we put everything here. This is an example of why we went to this methodology. We've been operating this Altar wash since 1992. In that time period, we are only able to get to the site once to measure a direct measurement, and that was at 569 CFS. And we had an indirect measurement that we did after a flow event that was 3,270. So the rating curve, which the data from this site was considered poor, was made up of just the 2 measurements. So what we decided to do was go ahead and we installed 5 CSA sensors in this one because we wanted to use the lower 3 to actually calculate the discharge, but the upper 2, I also wanted to put those in because they had the roughness in the channel was much different than the other lower sensors. So I wanted to put those in so that we could evaluate the channel roughness with those. So this is the first year that we put these out. We had 10 flow events, which you remember we only had two measurements prior to this. Put this in, we were able to get 10 flow events so we have now 10 measurements to add to the rating curve. And you can see these hydrographs that were generated from these different sensors in calculating the discharge. So here was the rating with the two measurements. We had 500 and some, and then 3,270. So this is what we had for over 20 years as our rating, and it was considered poor. When we were able to put in these continuous slope area, all of a sudden we have 10 measurements, 10 additional measurements, and then it better defined the rating. We feel that with these additional measurements that the accuracy of this site went from poor to fair. Now, the one problem that we don't have, we're still estimating what the end value is. If we can use the particle tracking, if we can get out there during a flood, we can fly the drone over this reach, and we can make a measurement with the particle tracking, we can improve the accuracy of this site, because then we can go ahead and we'll know what the discharge is, and then we can calculate our end value. And when we have that calculation, that will make the accuracy of our site much better, and we should be between fair and good at that point. So that's what our hope is. So we're using the particle tracking software with the CSA method to measure Manning's end and discharge. And what you can see here, we've done a lot of work here. We've flown this, and we're doing. We have 2D model here, and we've done quite a bit of work here with the drones. In October 1st, 2018, last year, we were just out in the field. We were at another location flying the drones, and then it just happened that this flow event occurred. And so we were able to very quickly go out to the site and make particle tracking measurement with the drones. And also we had a crew out there with this crane making a direct measurement. So we have a direct measurement with this equipment, along with flying the drone over 3 continuous slope area cross sections. And so this is a view from the drone. This is one of the JPEGs that I took from the video of the drone over one of the CSA sensors. And so this is where I processed the discharge for this flow event using this cross section. So the video provides the velocity. We have a sensor that's on the bank here, and it's measuring the stage. We've also shot the cross-sectional geometry. So with the stage sensor, we know what the area of this flow is. And with the particle tracking, that'll give us our velocity that's needed. And so we get this velocity by running it through the river software in the PIV lab. And that's what I'm going to go over next. The river software was developed by Antonio, and I'd slaughter his last name, but he's a doctoral, he did this for his dissertation, and he's been working with the USGS in developing this river software. And this is the first time in 3 years that I can say that the software is ready to be used. They got all the bugs out. They've made it so that you can go through it competently, that you're going to get good results. So this is a river software. You use this, you shoot your video over your cross section, or you shoot your video that includes if you're on the bridge, you take your video from your cell phone, and then you process it here in River. And this is image sequencing. So what it does is it takes the video and it's going to break it down into frames. And so normally a video shoots about 30 frames per second. So in this case, you're able to select the frame rate. I know that this is a high gradient stream, the velocity, flow velocities, over 6 feet per second. So using the raw 30 frames per second works fine for this application. If the velocity was less, then you'd want to use less frames per second. And you can see that we have 0 to 51 seconds of video. What I do is I use about 30 seconds, which produces 900 of these JPEGs that'll be used in the analysis, which is more than enough. So you initially open up River, you go ahead and run your video through it so that that River will now create these 900 JPEG images that you'll load into PID Lab to do the analysis. So now I'm opening up the PID Lab. I'm going to load in the images. And so you have to select the directory where River put these images, and then you have to select the images that you want to be processed. You had to add them into the software and then import them. And I'm going to go through this pretty quickly because all this is in, I mean, you're not going to retain going through this. But this is inside PID Lab. What you want to do now, the next step is to identify the area that you want the velocities calculated. So this ROI is how you identify that. And the ROI is the blue box. You can kind of see it up here. It goes through this red area. This is the area that I want the software to compute velocities. You also mask areas that you don't want to have processed. In this case, the vegetation. I mask that so that it's not processed in the velocities. If you don't mask it, then you will get that will be processed, and you know, that's not desirable. The next thing is the image pre-processing. There's two filters here that enhance the images so that now the software can pick them up better. And then this is the PID settings. These two boxes. These boxes represent the size of the area that's going to be compared from each slide or each frame to frame. And there's going to be hundreds of these little boxes all the way through here, and I'll show you. See, each one of these vectors represents those boxes. So the previous slide just shows you the area that each one of these vectors was determined by. So you can make this bigger or smaller it depends on your velocities associated with, with the flow event. Again, this would be something that Frank Engel is working on, how to determine what size you should use. I look at it when I'm applying this and see if it's bigger or small enough that I can cover this area effectively to produce these velocity vectors. I think this is a good distribution of velocity vectors. So then you do an analysis on the velocity vectors, and then you run it through for the whole 900 frames. And you get these vectors that are caused by waves falling over, and so you want to screen these out. So what you do is you go into the vector validation, and there's you select your velocity limits, and this allows you to take these out, to screen them out. And so you can see I selected it. Now the orange, you have the orange vectors that have replaced some of these that are that don't quite fit what we want. And then we go ahead and go into the plot function to calculate the mean vectors. So we're at the final step here. You go in the plot. What we want to do, we want to finish this session of PIV lab by calculating the mean vectors. So now this is the calculation of all the 900 JPEGs in the analysis done on those, and this gives you your mean vectors for those 900 JPEGs. And so now we're ready to go ahead and save this, and we're going to go back in the river. So we go ahead and save this PIV session, and then we're going to read this PIV session back in the river. So PIV went ahead and did the velocity calculations. Now we're going to go back in the river, and we're going to use that. We're going to calibrate, the video in river. We're going to do the discharge calculation in river. So you have to select the background image, and you can do that automatically. Then you load. This is your reference image, and in this case, I have 2 points because I'm going to use the drone video. And so basically, I identified the length of that distance between those 2 points, and I know the distance between those 2 points is 59 feet, 59.7 feet. And so this is now putting in this value calibrates the video. So now it also now wants you to identify the region that you want to be orthorectified. And I'll show you what that is. This is a region that you're interested in to have that rectification done for. So this is now calibrated to that distance. And then it asks for the frame rate, and this was it's a multiplier of when you use 30 frames per second, then it's 33.33 as the frame rate. So now it goes ahead and calculates your orthorectified velocities. And then you want to do is you want to identify where you're going to put the cross section. So I'm going to ask you for the original image, and that's what I did. And so I identified it over my 2 reference points and identified it as that's cross-section 4. And if everything's working correctly, you get these nice blue vectors that show the velocity vectors and direction. So now we're going to calculate discharge. So now we bring in this area comp, which is a very nice addition to River. This didn't exist in the last couple of releases. So you can see in this area, you can see the velocities that are associated with that video. And you can see it got up to 10 feet per second. So now what I need to do is I need to bring in my channel geometry. And so I'm going to import the channel geometry. And then it asks, you know, questions about the file that you're importing. And whether or not it's depth or elevation. In this case, it's elevation. And then now you can see the cross-sectional area, or the cross-section for this continuous slope area 4. Now, the next thing you have to do is put in the gauge height, which is the stage. So this stage was 3.96 or 3.95, and then you can see where it, you know, you see it here where it reaches in the cross section. The thing that we have to do is, you can see that this cross section, this main channel where the flow was, is offset. And it's offset by about 57 and minus 57. So I have to go up in here in the starting station. I have to put 57 in here so that the velocity profile is matched up with the channel geometry. So I put the 57 in. It went ahead and so now you can see that the channel geometry, or the velocities have been shifted over, and they'll match up with the channel geometry. The next thing I have to do is I have to change this mean velocity coefficient, and I put in 0.85 for that. And then you compute. And so this is the discharge that was calculated using the velocity from the particle tracking and the geometry and area that was recorded by CSA4. And so that's it for the presentation. I just wanted to show you how this software works. And this compared pretty good with the direct measurement. They weren't done at the same time, so I had a little problem with that. And so I couldn't make a direct comparison, but they're pretty close. So that's my presentation for this morning.
Thank you very much, Chris, for the presentation. I see Mark had to leave us. I personally find this fascinating. I can see how we can definitely take some of the thinking behind this and apply it to Southern Africa. Just, you know, by way of, I'm sorry, as a program coordinator, I have to come to the nitty-gritty of life. And when you say that, you know, when you go back to the continuous slope area mapping system and the sensors that you use, and you call them inexpensive, and you think of it as a very cost-effective method of measuring, which I can see why, but besides that, I mean, how, like, indicatively, how much would it cost to set up one of these points in a river stream, in a river channel?
Well, it cost me $35,000 to set up a USGS gauge, and it would cost me $3,000 to set up one of these. So about 10 times less. So if you know, to set up the whole system so that there is one point of measurement with the sensors that you showed,
would be roughly $3,000.
Right. And that would include the barometer, because you have to have that sensor plus a barometer sensor.
Yeah. Of course, sensor plus the barometer, of course. Yeah, I remember that. Okay. Well, you're quite right.
That includes our overhead. So Mark knows that. It can be. You can probably say, it could range from 2,000 to 3,000. Yeah,
no, that's fine. But I mean, just roughly to sort of, because I mean, if I were to say to the government here in South Africa and say, look, if you do this, you get almost like a constant flow of data, because I mean, I've been learning so far by interacting with governments that most data points in South Africa, at least, they go and measure twice a year. So you have results of every 6 months, and that's when you're lucky. Sometimes you don't even have verification. So, and that brings me back to my other question. How do you get the data? So you put those sensors in, and then are they Wi-Fi connected to a cloud, and they give the data in the cloud, or do you have to go and how does that work?
Well, that particular sensor, you have to take it out and you hook it up to your laptop. It does not transmit. It doesn't have any telemetry. So
you have to go there.
And so if you're going to go inexpensive, telemetry is very costly. So if you don't have any data, this is a good way to at least start building on it. Now, if you want telemetry, that adds additional cost to it.
Yeah.
And that could be, and I don't know what type of system would work in South Africa, but this is just for collecting flow data. And the one sensor is good if you're going to have someone do the particle tracking. But if you're not going to have the particle tracking all the time, if you put in additional 2 sensors, that's where the continuous slope area method actually calculates the discharge. In our case, calculates discharge every 5 minutes.
Wow.
Now in America, we're fortunate because I have 225 USGS sites with telemetry. But in the state, the counties have 1,000 sites with telemetry. So I could go to one of their sites and install one of these CSAs and provide them with a more accurate rating curve so that they operate their gauges for flood warning. And so this would be a way to improve their accuracy of their sites.
Absolutely.
So if there was a site that was, critical for flood warning, and they wanted to put telemetry for that, this would be a way to calibrate that flood warning gauge.
Yeah. Yeah.
So if you wanted to...
So right now here we rely on weather station for flood warnings. It's not entirely accurate.
Well, the thing is there's a lot of different ways to do telemetry. There's inexpensive ways. There's more expensive ways. But if you want, that single sensor would be $3,000, but you could add the additional sensors for about $2,000 a piece. So if you wanted a complete gauge that will compute discharge, you need those additional sensors to be standalone.
Yeah.
So you would add an additional $4,000 to that, so you'd be up to around $7,000.
Yeah. And the software, that river software?
The software is free.
Oh, okay.
We developed a method. Yeah, we have videos that if you search on the web for continuous slope area or reach scale monitoring, you'll see our team, and we've developed the method and the procedures, and the software and everything, and that's all free.
Yeah, interesting. Thank you for this. I found this presentation fascinating, and I mean, I'm sorry Mark left, but he was actually quite right. It's very relevant for us as we try to figure out a way to improve our understanding of our river flow in the least, let alone the system. And I like the fact that, you know, like you're testing it in Arizona, which is a sort of dryish country, I would imagine. So similar sort of climate variability that we have here, and similar river variability that we have here, with rivers that don't flow all the time. You know, they spend
Right.
part of the year really dry, or where the stream is underground, so you can't really monitor it. Thank you. Are there any questions from the audience? Rodolfo, Luis, Tato, have you got any question for Chris? I see Rodolfo. No, he hasn't got any more questions. He's still the same. Okay. Chris, we have recorded this conversation and this presentation, so we're going to just edit it and make it available on our YouTube channel, and send you the link as well. I really would like to thank you for spending this hour with us, and I'm sure that once we upload it and we share it with our partners and our teams, there will be some follow-up questions. So I might redirect people to you as things progress, or I might call you back in to give a presentation where I make sure that all the people that are part of this research will be present, so they can actually understand what is happening in other countries, and particularly with the work of USGS. I mean, just from the presentations that we've had through Mark, with all your colleagues, it's an amazing work. So thank you for sharing it with us. Oh, I see we have a question from Louise. Sorry, just a second. Oh no, she said no, saying thank you, super interesting. Thank you, Louise. I appreciate that. I'll keep on sharing the webinar sessions on the group on LinkedIn that we have. Like I was saying earlier, Chris, thank you very much for your time with us. Thank you for this presentation.
You're welcome.
And if you could just email the presentation to either me or Liz, that would be fantastic, because then we keep that in our repository as well.
Okay.
Thanks again.
Well, thank you for having me.
Thank you for staying, and I wish you a wonderful day further.
Okay.
Okay.
Bye, everyone.
Okay.
Talk to you next week.
Bye.